Next, one-dimensional wave equation. Consider a uniform elastic string of length L stretched tightly between 2 points O and A. One of the endpoint is O and another endpoint is A, and taking OA along x-axis, O is considering as origin, and then draw a perpendicular line through O to the line OA, and consider this line as y-axis. Now a tightly stretched string is slightly displacing through a distance p p dash from its equilibrium position OA. OA is taking along the x-axis. This is tightly stretched string between the 2 points O and A. O is one endpoint, A is another endpoint. O is taking as a origin, and we are drawing a line perpendicular to the line OA through the point O and taking this as a y-axis. After that, we are displacing slightly the tightly stretched string through a distance p dash from its equilibrium position OA. Now we shall find the displacement y as a function of the displacement as a function of the distance x and the time t. Therefore, y is a function of x comma t. If we model this physical phenomena into a mathematical equations by making some assumptions and Newton's second law of motion, we will get the partial differential equation. Dou square y by dou t square equal to c square into dou square y by dou x square, where c square t by m, where t is the tension in the string at any point and m is the mass per unit length of the string, subject to the conditions y of 0 comma t equal to 0 for all t greater than 0. Here at this end point O origin, the displacement at any time t is 0. The displacement at any time t equal to 0. So that is one boundary condition. Another boundary condition is y of L comma t equal to 0 for all t greater than 0. Here at the another end point, the displacement at any time t is 0. At any time t 0. So the length of the string is L. So this is L comma 0. This point is 0 comma 0 origin. This point is L comma 0. So length of the string is L. So therefore y of L comma t. So this is one endpoint, this is another endpoint. So these two conditions are boundary conditions. Y of 0 comma t equal to 0 for all t greater than 0, y of L comma t equal to 0. These two are called end conditions or boundary conditions. End conditions or boundary conditions. Now another condition is initial conditions. Y of x comma 0 is equal to function of x for all 0 less than or equal to x less than or equal to L. So this is the initial displacement in the string at any point x at time t equal to 0 from its equilibrium position. From the equilibrium position of the string, we slightly displaced the string through a distance p dash. This curve is y of x comma 0 is equal to f of x. That is called initial condition. Another initial condition is initial velocity in the string is also 0. Initial velocity at any point x at time t equal to 0. Therefore, another condition dou by dou t of y at x comma 0 is g of x. We are assuming that. So if it is released from its equilibrium position after displaced through a distance p dash, then initial velocity is 0. Sometimes in the function we will have initial velocity as a function of x. So we are assuming dou y by dou t at x comma 0 is a g of x for all 0 less than or equal to x less than or equal to L. So it may be 0, or sometimes uh, it has some velocity. So initial velocity may be there in the string. With a certain initial velocity we may release from the equilibrium position. So there we will have g of x. Therefore, these two conditions are called initial conditions. These two conditions are called initial conditions. These two are called end conditions or boundary conditions. These two are called initial conditions or initial conditions. There is no another name for this initial, this end conditions. There may be call it as a boundary conditions, but these two are only initial conditions because time t equal to 0. At time t equal to 0 the condition is given. Those conditions are called initial conditions. Therefore this is a initial boundary value problem. These partial differential equations can be solved by the method of separation of variables, as we discussed earlier in the previous classes. Consider a uniform elastic string of length L stretched tightly between the 2 points O and A, between the 2 points O and A, and displaced slightly from its equilibrium position. OA. Here, consider a uniform elastic string of length L stretched tightly between two endpoints. One of the endpoint is O and another endpoint is A, and then displaced transversely through a distance, small distance p dash from its equilibrium position OA, from its equilibrium position OA. Now taking the point O as origin and OA as x-axis, draw the line perpendicular to OA and consider this axis as a y-axis. Then the displacement y is a function of the distance x and the time t. Taking the end O as origin, OA as the x-axis, and the perpendicular line through the point O as the y-axis. We shall find the displacement y as a function of the distance x and the time t. That is, y is a function of x comma t. Then the small transverse vibrations of the string is governed by the one-dimensional wave equation. Dou square y by dou t square is equal to c square into dou square by dou x square of y, where c square equal to t by m. T is the tension in the string at any point, and m is the mass per unit length of the string. subject to the conditions y of 0 comma t equal to 0 for all t greater than 0. Second one, y of L comma t equal to 0 for all t greater than 0. One endpoint 0. There is no displacement at the end points. So displacement at any time t at origin is 0, and another endpoint L, there also there is no displacement at any time t in the string. These two conditions are called end conditions or boundary conditions. End conditions. Now third one, initial displacement y of x comma 0 is equal to f of x for all x lies between 0 less than or equal to x less than or equal to L. So initial displacement in the string from its equilibrium position should be in the form f of x function of x after slightly displacing from its equilibrium position through a distance p dash as shown in the diagram and explained earlier. Fourth one, initial velocity dou by dou t of y of x comma 0 equal to g of x for all 0 less than or equal to x less than or equal to L. If it is released from its rest position, then it is a 0, or after the equilibrium position, initially we may release the string with certain velocity. There it is equal to g of x. These are the boundary conditions, and these two are initial conditions. These two are initial conditions. These two are called initial conditions. Here we do not require the modeling of this partial differential equation from the physical phenomena, given physical phenomena, transverse vibrations of a stretched string. So if you model by applying the conditions and Newton's second law of motion, we get this partial differential equation and its boundary conditions. We do not require the modeling of this partial differential equation, but we require here the solution of the one-dimensional wave equation. We know that how to solve the second order partial differential equation, which is solved by the method of separation of variables. So next we will find the solution of this one-dimensional wave equation by the method of separation of variables.